Alright, so now what we're going to do is we're going to use what we've just learned about the mole concept and try out a few examples with it. Okay, so say we're given a sample of sodium. We're given a sample of sodium, a big clump of sodium, and we're told to weigh it, told to find out its mass, and we find out that its mass is 16.4 grams. Okay? And so what we want to do is we want to find out the number of mole of sodium. Okay? So the way we're going to do this, okay, so we're going to denote the number of mole of sodium, and so we're going to denote the number of mole of sodium by little n, and then in brackets sodium. So this is the best way, this is the easiest way I found to keep track of what we're talking about, because you can get lots of little n's and big n's and stuff flying around. So we're going to write the mole of sodium as little n and then in brackets Na for sodium. So that's what we're trying to work out, okay? And we know from experience, from what we've just learnt, that this equation, the mole of a substance, is given by little n equals little n equals little m over big M. Mole equals mass divided by molar mass. Okay? So now what we're going to do, we know that the mole of sodium is therefore going to equal the mass of sodium given by little m Na divided by the mole mass of sodium. Okay, and so what we do is we look at our periodic table to find out the molar mass. So we know that the molar mass is the same as, or is equal to the mass number of an element. Okay, and so the mass number, or the atomic mass of sodium is 23. And so we know that the molar mass of sodium is 23.0 grams. Okay, and now we know that, as we've just tested, we know that the mass of sodium is 16.4 grams. So what we can do now is we can figure out the mole. So we substitute these two values in up here. So we do this. We say this is equal to 16.4 grams. It's important to keep track of the units, and that way it's a good way to know that you've done the calculation correctly. So 16.4 grams divided by 23.0. Now, we define the molar mass as the number of grams in every mole of a substance. So the obvious way to give that a unit is grams per mole. Okay? So they're the units. And so we put this into our calculator. We say 16.4 divided by 23 is equal to 0.71. Okay, so now we know that the mole of sodium is, as we've just calculated, 0.71. Okay, and so we've calculated. We've been given a sample of sodium. We've measured its mass using some scales. And we've come out with this number. This is the number of mole of sodium. And so what we want to do next is we want to figure out the number of atoms. Okay, and the way we're going to do that is we're going to describe the number of atoms as capital N, and in brackets sodium. So what is that equal to? Okay, now again from the last video, we found that the number of atoms of a substance is equal to the number of mole of a substance times Avogadro's number, which is the number of atoms in 1 mole. Okay, and so we know from up here that little n is equal to 0.71. Okay, so we can sub that in, straight in from our last answer. Okay, and no, here when we're doing calculations like this, where we've done part A, and we've come out with a number, and we've rounded our answer to 0.71. So the actual answer was 0.71304, etc. Written down 0.71, we've rounded our answer. But it's important to remember that in this instance, when we're using that answer for the next question, we can't use the rounded value. We need to make sure we use the full value, okay? So maybe write that down in the corner of the page, or keep it in your calculator or something. But make sure you keep track of all of those decimals, okay? So I've written that here as 0.71 ... So we're using the rest of the decimals times Avogadro's number, Na, which is 6.02 times 10 to the 23. Okay, and so that into our calculator, and we get that n of Na equals, sorry, not n, that's the wrong Na. Alright, n of n little a, to denote sodium, it's an easy mistake to make, is equal to, so put it into our calculator, so we got 0.71, we're keeping the rounded values, okay, times 6.02, okay, so 4.29 times, now I haven't put, what I've done is I've calculated, I've put this part into my calculator, okay, and I've left the 10 to the 23 out. Now what you'll often have to put, you need to put the 10 to the 23 in still, but in this case, it still works out that the simplest way, it comes out as 4.29, and we keep the times 10 to the 23. So it's 4.29 to 2 decimal places times 10 to the 23. Okay, and so this doesn't have a unit per se, this is just the number of atoms. So I guess you can kind of think of the number of atoms as a unit, but it doesn't have a unit in the sense that we have grams or mole. And so what we've done here is we've taken the mass of a substance, we've been able to calculate the number of mole of that substance, and then from there we've been able to calculate the number, the exact number, well, here to 2 decimal places, but if we want, we can have the exact number of atoms in that sample. And so that's how we use the mole concept to calculate the number of atoms in a sample.